call your name. If your phone's still not where it should be, please put it there. Julia, Daniel, the other Daniel.
Here.
Olivia,
Here.
Samantha,
Here.
Julian, Claire, Allison,
Here.
Lauren, Randall, Samantha,
Here.
Brienne,
Here.
Nicole, Cassandra, Annika,
Here.
Christina,
Here.
Decus,
Here.
Alexandria,
Here.
Annabelle,
Here.
Ryan, Ariana, Leah. Leah, you here? No. So today's a review class, and it's a full block, so we have hopefully sufficient time to go through the material. Just a little bit about the test. Obviously, it's not gonna be Wednesday. It's gonna be the first full block after today, whatever that is, okay? I haven't looked at the schedule. I don't know when that will be, but in the interim, we're not gonna have review after review. We're gonna move into chapter 6. So that way, we're still covering material. And then in the unlikely event we ever have a full class, we'll have the chapter 5 test, all right? The test has 32 multiple choice questions. And let's see, 1, 2, 3, I think 6 or 7 written response. It's out of 67, 32 from part 1, 35 from part 2. You're not gonna have to calculate wavelength or energy associated with the stationary states, but you do need to remember a couple equations. Not so that you can calculate with them, but because they are significant in our discussion. Frequency wavelength to the light. Another one is this. And you may or may not remember that because that's so small, that means that neither the Heisenberg uncertainty principle nor the Broglie's wave equation for the wavelength of a macroscopic particle need to be concerned because h is so small. This is probably obvious, but beyond that, if you need de Broglie's equation, I'll give it to you. Here, that's velocity, so it's not frequency. And that is where that came from. Actually, including that one as well. You should be able to write short form configurations with or without core notation for atoms and ions. And remember, if you're writing the configuration for a cation, you're going to remove as many electrons as the magnitude of the positive charge has from the highest energy orbitals on the outside first. Now, why did I say highest energy on the outside? Well, let's say you're removing something from the 5p and 5s, you start with the 5p before the 5s. But the principal quantum number always tells you what's on the outside. So if you got, say, 5s2, 5p2, you're going to take the 2 5p away before you take the 2 5s away. And that's the benefit of writing it littlest to biggest beyond core notation, which is what the periodic table does. Now, it's not that imperative that you do that for anions, because all you do is keep adding electrons. You just add as many extra electrons as the charge requires, and you just keep doing it in the order that the outlaw principle specifies. You also should also be able to draw orbital diagrams for atoms and ions, anions or cations, okay? When you write the short form configuration, past the core notation, you can write a littlest to biggest, because that dictates behavior. But when you're drawing orbital diagrams, you can't change the energy that you fill, okay? You just have to remember, if you're drawing an orbital diagram for an ion, where the extra electrons get added to, or where the electrons get removed from, if it's a cation, okay? I'm not going to expect you to remember dates, but I will expect you to remember major contributions of the players that we discussed. So the whole chapter is about our understanding of atomic structure. So ask yourself, what are the major contributions that some of the major players made? Chronology does matter. In other words, Rutherford came after Thomson, and Bohr came after Rutherford, that type of thing. But it's not so much the dates, it's their contribution. And remember how sections 5.1, 2, and 3 are structured. 5.1 ended with the dilemma. 5.2 temporarily solved that dilemma, but 5.2 ended with a dilemma. That was solved by section 5.3. So specifically, the nuclear model of the atom was unstable. Why? What did Bohr do to save it? Bohr's model was insufficient. Why? How did quantum mechanics fix that? And think of the players that we discussed. What did Louis de Broglie have to say? What did Heisenberg have to say? What did Schrodinger do? That type of thing. And the other thing is that whereas there may be calculations involved, for example, at the end of 5.1 we talked about spectroscopic data, the percent abundance, relative mass, that type of thing. The questions are not going to be primarily what you've seen before on previous tests, so it's dramatically different than stoichiometry. Here it's explain, discuss, describe. And remember, even if the theory doesn't make sense to you, even if you can't wrap your head around how something can be a particle and a wave at the same time, and to be honest, how it appears depends on what questions we ask. If we ask it to behave like a particle, an electron, it does. It has a charge to mass ratio. Anything with a charge to mass ratio has a mass, ergo it's a particle. But if we ask it to behave like a wave, it'll do that too. It generates diffraction patterns. So the question is, what is it? Well, it's both until we ask it a question. And that's the whole idea of, I don't know if you ever heard the analogy of Schrodinger's cat. An electron is both. It's a particle and a wave at the same time. How can that be? Well, it depends how we look at it. In other words, the very act of asking it questions dictates its nature, which is a weird thing to wrap your head around. But if you can't, relax. The fact is it works. And the dilemma of quantum mechanics is something that physicists much smarter than you and I are have wrestled with for a long time. As it turns out, it's the best we can do for now. And that's something that Einstein could never live with. He does not throw dice. And that is his way of basically summarily rejecting Heisenberg's uncertainty principle. That tells us that at its most basic level, matter seems to be governed by the laws of probability, which upset him a lot. And that historian from Harvard put it really well, that Einstein believed in a universe that was deterministic causal, where with sufficient information about the present, you should be able to mathematically, with 100%, predict what was going to happen in the future. And quantum mechanics says you can't do that. So there's a lot of stuff in Chapter 5. And your understanding of Chapter 5 is going to help you a lot in post-secondary. Because professors will assume that you know what orbitals are. They'll assume that you can draw orbital diagrams, write short form configurations, that type of thing. Okay? So, enough of me. Questions? Ask away. Yeah.
When we talked about like the cathode ray tubes and stuff, do we mention the specific parts of it or just the impact it had?
The specific parts of it, what do you mean?
Like how it formed like the different components of the ray tube?
Of a cathode ray tube?
Yeah, or just like what it did.
Not really. I mean, all really a cathode ray tube is an electron gun. You burn electrons off a filament with an accelerating voltage of 10,000 volts. So what's happening is the atoms in the metal filament, you're heating it to a point that you're burning electrons off. You're ionizing that atom. And then the electrons shoot out of it. That's really all a cathode ray tube is. It's an electron gun. By modifying the Crookes tube, Thomson was able to calculate the charge to mass ratio for these mysterious particles. And the fact that it has such a big charge to mass ratio suggested that the mass of whatever these things were was really tiny. So, but no, you don't have to diagram a cathode ray tube. The business end of it is basically it's an electron gun. All right? Yeah.
Do we have to explain like the experiments of the gold foil?
Wait, what?
Will we have to explain the experiments, like the gold foil experiment, and like write it in depth, or is it just?
You have to know what they did. In other words, what does it mean when virtually all of the alpha particles that go through a gold foil go through, as if there was nothing there? What does that mean? Well, it means nothing's there. So that means that most of the volume of an atom is empty space. So yeah, you do kind of have to understand what that told us. That's why we went into it in the detail that we did. The other thing, and I think sometimes I am remiss here, is I do too much for you. I don't know how much you guys are used to actually reading the book. Get a highlighter, read the book. It was written to be read. It's not simply what I teach is all you write down. Read the book. The information that you need is there. Now sometimes I go beyond the book, but read the book. It was written, not just what I wrote, but what the other teachers wrote. It was written by teachers. So it's probably a little more user-friendly than some of the textbooks you're going to get in post-secondary. That's why you should take this with you when you go to post-secondary. I've had a number of students tell me that the books in grade 11 and 12 helped them as much as their textbooks in first year. So read the book. It's yours. Write, post-it notes, highlights, notes in the margin. By the end of the year, it should look like crap, but use it. That's the whole point. And everything we've talked about is in there. Now, what isn't in there in detail are the 5 exceptions that we talked about. Chromium and molybdenum, one away from a half-filled D sublevel, those are S1, D5. And then copper, silver, gold, one away from a filled D sublevel, S1, D10. There are more exceptions than that, but those are the 5 that I'd like you to know, okay? So I mentioned that those 5 exceptions exist, but I didn't go into detail into what the actual exceptions are in the book. That's why I did it in class, okay? Don't forget to bring a ruler because you will have to generate that diagonal diagram, unless you can tell by looking at the periodic table. And if you understand the periodic table, you don't need the diagonal diagram, but you can't miss if you write on the diagram, okay? And that just tells you the order you fill orbits. That specifies the order given by the L-Pop principle. Yeah.
On page 247,
Which page?
247,
Yeah.
can you go through, section
Question.
7?
Page 247.
Yes.
Write the notation for the following ions. Okay, so this is a standard atomic notation, right? A 3+ cation with 80 electrons and 127 neutrons. Okay, if it's a 3+ cation, we've taken away 3 electrons, right? So how many electrons did the atom start with? Well, if it's got 80 and we took 3 away, it must have had 83 as a neutral atom, which means that's the atomic number. So you know the number of protons, you know the element. 127 plus 83 is the mass number. 83 is the atomic number. And then go to the periodic table, find element 83. And don't forget to put the 3+ charge on the top right, okay? B and C as well.
I would like B, because they didn't match the answer key.
The answer key might be wrong. More than one student has mentioned that. So which one didn't match?
A and B.
A?
A and B.
A and B. Okay, let's do B. A 1- anion with 54 electrons. So that means the atom has 53, and it means it's got 53 protons. So 53 protons would be iodine. So 53 plus 78 would give you the mass number on top, and then 1-, which makes sense because iodide's stable ion is 1-. Yeah. And C is okay?
Yeah.
Okay. Yep.
Can you just clarify for me, like, why Rutherford's atom model would collapse?
Why it was supposed to collapse,
Yeah.
according to classical physics, because an orbiting electron is an accelerated charge, because it's changing direction. So, because velocity is a vector quantity, whether we change speed or direction, we're accelerating. That's what acceleration is, rate of change of velocity. All the experiments that were available to physicists at the end of the 19th century showed that accelerating charges always radiated energy. And we can put electrons in a wire. Alternating current in a wire generates radio waves. That energy has to come from somewhere. So according to classical physics, because an orbiting electron is an accelerating charge, it should lose energy. If it loses energy, it slows down. If it slows down, it collapses into the nucleus in a fraction of a second, which means matter should collapse. So an atom was unstable according to classical physics. Bohr's temporary solution to that was to say that as long as the electron is in these allowed energy states, or stationary states, it didn't lose energy. He didn't know why, but he said that had to be the case. The why was provided by de Broglie, who said if a wave can act like a particle, as suggested by Max Planck and confirmed by Albert Einstein, perhaps a particle can act like a wave. And if an electron does act like a wave, then perhaps the reason that the electron doesn't lose energy is because it's a wave and it's in a standing wave pattern in each of these allowed energy states. But if you treat it as a pure particle with a negative charge, the atom should collapse. So the first video you saw, they didn't mention de Broglie's name at all. And that physicist had said, in other words, an electron is a point particle, and the probability of finding it is given by a wave. That's true. But if it were simply a point particle with a negative charge, matter would collapse. So they conveniently ignored de Broglie, and they made it sound like Schrodinger was the first person to think of the electron as a wave. They didn't mention de Broglie's Nobel Prize, so they left out a whole part of it, perhaps because it was too weird. But that physicist from MIT, he never said that. He never said, I understand it's just simply a point particle and the probability is finding is given by a wave. But it's interesting when he used the laser beam and the narrow slit to prove Heisenberg's uncertainty principle. Whether or not they knew it in the video, they were actually showing particle wave duality. Because a laser beam is a light wave. If you're narrowing the slit, the fact that that image gets wider and wider and wider, that's a diffraction pattern. So by treating the laser beam as a bunch of photons, he's basically proving Heisenberg's uncertainty principle. So he's saying that waves can act like particles. Okay, the electrons do the same thing. Particles act like waves. So you can't explain stationary states, you can't explain energy levels, if you want to put it that way, without incorporating standing waves. So that's probably more of an answer than you needed, but there it is. And remember the three consequences or important aspects of the quantum mechanical view of the atom. You should remember those. The very first one begins with the energies of electrons in atoms are quantized, courtesy of Bohr. Why? Because of their wave nature, courtesy of de Broglie. Meaning, the only allowed energy states, or stable energy states, if you will, in atoms are those in which we can maintain a standing electron wave. That's number one. Number two is stating the Heisenberg uncertainty principle. And make sure when you state it, that you don't say it's impossible to know where a particle is and where it's going at the same time. It isn't. It's impossible to know where an electron is and where it's going at the same time. Quantum mechanics, the two words, quantum means really small, mechanics means dealing with the world of the really small. So this is only applicable to the world of the really tiny. Not to the world of the really big, but in the world of subatomic particles, we need a way of dealing with it. That's what the mechanics part of quantum mechanics is. And then the third one, of course, is kind of the compromise, courtesy of Schrodinger. If electrons have a wave nature, and the only thing you can say about them is probability, then how do we describe atomic structure at all? Well, the existence of atomic orbitals. And then you have to tell me what those are. And there's several points that you have to include. Those regions in three-dimensional space, so they're not a path, they're a volume. A region in three-dimensional space where, around the nucleus, where electrons with a particular energy are most likely found. So there's 4 points to it. All right? And that ended section 5.3. Then what we did in 5.4 is we applied it. Then we said, okay, let's do short form electron configurations. Let's do orbital diagrams. And when we did that, that started to make a lot more sense. And that's what section 6.1 is all about. It's about the periodic table. In a nutshell, 6.1 is about the most important thing to know about the periodic table. That elements in the same family have similar behavior because they have similar outer electron arrangements from a quantum mechanical's perspective. Section 6.2 is about the second most important thing to know about the periodic table. As we travel left to right or top to bottom, there are regular and predictable changes in these properties. Those are called periodic trends. Okay. 6.3 is about bonding. 6.4 is about shapes and behaviors. 6.4 and 6.5 are about that. Affectionately known as Vesper theory. Valence shell, electron, pair repulsion. That's what the end of chapter 6 is about. Okay? And that's gonna lead us into chapter 8. If we ever get that far. What else? Yes?
On page 258, could you go over question
258, question 8. I don't know. I hope so. 'Cause I wrote it. Okay, I can show you that. It's better in color. Remember, an emission spectrum are the bright lines we see when excited electrons, after absorbing energy, have returned to their ground state. Okay? So because in a collection, say, of hydrogen, we've got in any individual atom, there's only one transition happening at a time. But if you got countless atoms, all the transitions are happening. Okay? So whenever energy is absorbed from 2 to 3, red light is absorbed. So let's say we had a continuous spectrum, like a rainbow. A hydrogen electron going from 2 to 3 would plunk energy from that red end to go up. So we would see a black line where there was a red line in that part of the visible spectrum. 2 to 4 would be the blue-green line. 2 to 5 would be blue, 2 to 6 would be violet. That's the absorption spectrum. And the absorption spectrum is in your book. It's just that it's not in color. So we could have printed the book in color, but then it would have been $100. When the emission spectrum happens, which is what Bohr saw looking through those little spectroscopes, he saw what happened when the electron came back down. And then you see that red light released. So if you superimpose the emission spectrum, where the lines are released, onto the absorption spectrum, where the lines are absorbed, you regenerate that continuous spectrum. Guessing here, 5.1. Yeah, that's chapter 4. Okay, I gotta go here maybe. Alright, we'll get in there. There we go. So forget these two. Just turn the lights up for a second. So this is hydrogen's emission spectrum. That's 3 coming down to 2, 4 coming down to 2, 5 down to 2, 6 down to 2. When that electron absorbed energy, it went from 2 to 6. Okay, so going up, it absorbs that. That's why we get that little loss of the energy in the visible spectrum. Going up to 2, from 2 to 5, it absorbs that. 2 to 4, 2 to 3. When it comes back down, it gives that energy back. And the energy is what we see in the visible spectrum. If we took that and plunked it onto this, we'd simply get a continuous rainbow. That's all, okay? So the answer is you'd get a continuous spectrum showing all the colors in the visible spectrum. There's what we generally call 7 colors, even though they kind of all wash into each other, okay? And it can't be continuous. The emission spectrum can't be continuous because the energies of the electrons are quantized. They can't exist in any energy, okay? What else? Yeah,
Could you go over number 10 on page 248?
number 10. Silver has 2 naturally occurring isotopes. Calculate the percent abundance of silver 107 and silver 109 using the following data. Okay, that's the second type of calculation at the end of 5.1. One of them was, here's the percent abundance, here's the mass, what appears in the periodic table. The other one was for an element that exists as 2 isotopes, whatever isn't one is the other. So the percentages have to add to 100%. Another way of saying that is the fractions have to add to 1. So let's say that 20% of an isotope has this mass, 80% of the other has this mass. 80 and 20 add to 100, but 20% is the same as 0.2, 80% is the same as 0.8. So if you look at the second sample problem on top of page 245. Boron has 2 naturally occurring isotopes, just like silver. I can only ask this type of question for something that exists as 2. If it's not one, it's the other. So let's look how we solve that one and apply it to silver. If you look at the what to think about. So what appears in the periodic table is 10.81. Notice that that's closer to 11 than it is to 10, okay? Mass of boron 10 is 10.0129. Mass of boron 11 is 11.0093. Whatever isn't boron 10 is boron 11. So, the weighted averages of the isotopes yield the atomic mass of 10.81. The sum of the fractional abundances must be 1. So let's let X equal the fractional abundance that's boron 10. So the decimal amount, if you will, okay? Whatever isn't boron 10 has to be boron 11, and they have to add to 1. So if X is the percent abundance that's boron 10, 1 minus X has to be boron 11, okay? So if you look at the how to do it, and you compare it to the arithmetic on the bottom of the previous page, if you had the percent abundance, so on the bottom of page 244, we had 90.48% of neon is neon 20. So 90.48 divided by 100 is 0.9048. That multiplied by the mass added to the same products of the other isotopes give you what we have in the periodic table. So now look back on page 243 or 245. X is the fractional abundance that's boron 10. That multiplied by the mass plus the fractional abundance that's boron 11 multiplied by its mass has to give us what we have in the periodic table. So all we do now is just use a little algebra. 10.0129x plus 1 minus x times 11.0093 equals 10.81. We isolate x, we solve for it. Notice that we get 0.2000. That's why I picked it for the example. So if the fractional abundance of boron 10 is 0.2, that means 20% of boron is boron 10. What isn't boron 10 is boron 11. So 1 minus 0.2 is 0.8. That means 80% is boron 11, which makes sense because it's the mass on the table is closer to 11 than 10, right? Now, if we do the same thing for number 10, let X equal the fractional abundance, that's silver 107. Then 1 minus X has to equal the fractional abundance, that is silver 109. So we do it exactly the same way. And you know they have to add to 107.87 atomic mass unit. So, what would the arithmetic look like? Well, X equals the percent abundance, that's silver 107. So that times the mass, that's silver 107, which is 126.9051 atomic mass units, plus, what isn't silver 107 is 109, which is 1 minus X, and that mass is 108.9045 atomic mass units. And we know what that equals, because we have the information periodically, 107.87 atomic mass units. And then we just solve for X. And once we have X, 1 minus that gives us, and again, this is going to give us a decimal, but turn it into a percent by multiplying it by 100. Could you take it from there?
Yeah, I was just having an issue with the sig figs because it was
Don't worry
giving
about
me.
the sig figs. When all is said and done, you want 2 decimal places in your answer. So
Okay.
90, or let's say, what did you get for your percent abundances?
51.741, and
Rounded to 2 decimal, 54.74.
because that's what the book was giving me, and I was getting a longer one when I was counting the sig figs.
Yeah, like, the fact that this is so precise means that the periodic table is precise.
Okay.
The reason I left it to 2 decimals, that's what you have in your periodic table. So
Okay.
just stick with 2 decimals.
Okay. Thank you.
When you're doing a question like this, so I'm glad you asked it, because don't just do this. Tell me what X is. I don't know if you guys, if that's insisted upon when you're doing algebra and math, but don't expect me to interpret what it is you're saying. It has to be crystal clear. So what is X? Let X equal the fractional abundance, that's silver 107. Therefore, 1 minus X equals the fractional abundance, that's silver 109. As soon as you tell me that, then I know exactly where these things come from. And because you're asked for a percent abundance, you're gonna get a fraction, you gotta multiply it by 100 to turn it into percent, okay? And unfortunately, the detailed key isn't there, it's just what's the answer. And you should be able to do either of those types of questions. Either sample problem number 1 or sample problem number 2. I'm not gonna give you both, but you should be able to do either of them if I ask you. And for this type of question, I can't give you something that exists in any more than 2 different isotopic forms. Because that way there'd be multiple variables and that'd be too difficult. What do you guys, when's the last time you did any algebra in math? What grade? This grade? So you're doing, your guys are comfortable solving for X? Okay. There's a couple more of those in Chem 12 if you take it next year. So. What else? Yeah.
On page 254, it asks if there was any problem with calculating the wavelength of emission.
Don't worry about that.
Okay.
I'm not gonna ask you to calculate wavelength. And the only reason I mentioned this in the book, I just go through that to show you that it worked perfectly for hydrogen, all right? Basically to say that Bohr must have been on the right track because it worked so well. But no, I'm not gonna ask you to calculate lambda or delta U, okay? The arrow pointing up or down is the magnetic field resulting from the spin. So an electron has a negative charge, it's also got a spin. And then you say, well, how can it have a spin if it's a wave? Good question. It behaves as if it's a little negative particle spinning on its axis. So when we draw an up arrow, we're basically saying we have a counterclockwise spin generating a magnetic field in the up direction. It's not spinning up, that's the direction of the magnetic field from its counterclockwise spin. The arrow down tells us it's spinning clockwise. When you draw an orbital diagram, that's what those arrows represent. You don't have to worry about spin when you're drawing short form configurations. You only have to worry about it in orbital diagrams. And remember, that's courtesy of Wolfgang Pauli, who basically said that no two electrons in an atom can have the same set of 4 quantum numbers. And remember what the 4 quantum numbers tell us. The first 3 tell us about orbitals. First one tells us the size of the orbital, the size of the charge cloud, the energy level we're in. Second one tells us the shape of the charge cloud. In other words, is it an S, a P, a D, or an F orbital? The third quantum number tells us the orientation in space, which tells us not just the size of the charge cloud or its shape, but which way it's facing, its orientation in space. So for example, if we go 3D x squared minus y squared, the 3 is the principal quantum number. The D is the second quantum number. And the dx squared minus y squared is the orientation in space. So when you have the first 3 quantum numbers, you have the exact orbital that an electron is in. The fourth quantum number doesn't tell us about the orbital. We already know that from the first 3. The fourth one tells us the spin on the electron. That's why we call it a spin quantum number. And according to Pauli, if electrons are in the same orbital, obviously they have the first 3 quantum numbers the same. But then they have to spin in a different direction. So 2 electrons in an orbital, their magnetic fields cancel each other out, which has to mean that their spins are opposite. Okay? And that's the Pauli exclusion principle. And in the book, I think it's correct to describe it as the first rule or law governing multi-electron atoms. And we have to apply it as soon as we get to helium, because helium has 2 electrons in the same orbital, and they spin in different ways. Okay? And whether you draw the arrow with, the typical this or that, it doesn't matter. Most of the time you're going to see it written like that in the textbooks. Okay? What else?
On page 280, can you go over question 11?
Okay, not a bad question. And it's not a bad question because you guys are gonna have to do this, not this one necessarily, but you're gonna have to draw orbital diagrams. And whenever you're drawing an orbital diagram for an ion, or writing a short form configuration for an ion, start by writing what the atom would be, what the neutral atom would be. Then ask yourself, okay, am I adding electrons to that for a negative ion, or am I taking them away? If I'm taking them away, I gotta take from the biggest. If I'm adding them, I just keep going. So B says, use a highlighter to label the electrons that would be lost when the iron 3 cation forms. So that means draw the atom first, and then you're gonna take 3 electrons in. Now on the test, I might not just give you a blank page, I might draw the axes for you. But this, remember, is not distance from the nucleus. energy. It's not the same thing, yeah.
May I go to the washroom?
Yeah, go ahead. And you might wonder where, how you write the n equals 1, 2, 3. Draw the orbitals first and then put the n's in second, okay? So, that'll be the 1s. Two S. Now some textbooks put the 1s here and the 2p and then the 3d. Just do them vertical, okay? I don't want you to worry about side to side. 2s, 2p. So all I'm doing is following what the diagonal diagram would give you, okay? 2p. After 2p, 3s. 3p. And you might wonder how hard you have to go. Well, look in the table. 1s, 2s, 2p, 3s, 3p, 4s, 3d. So you only have to go to the 3d, okay? 3p, after the 3p we come to the 4s. And then we have, for the first time, the d sub 1, 2, 3, 4, 5. And you don't have to write, x, dx, y, dy, z, just write, all you need to know is that there's 5. Okay, but you do have to label like that, okay? So now that you've got those on there, now you can put in n equals 1. Put n equals 2 halfway between the 2s and the 2p. And notice that 3p is higher than the 3s but lower than the 3d. Put n equals 3 here. Level with 3p, and you can write n equals 4 up here if you want. And remember, because it's energy, it's not distance from the nucleus. So these are higher in energy than the 4, but they're inside the 4. That's why that's a 3 and that's a 4. Okay? So now let's draw the atom. An iron atom has 26 electrons. You know that because its atomic number is 26. So that periodic table, you're not going to get that. You're going to get the one in the book. So get used to looking at the one in the book. And notice, as I've said many times, we've separated that periodic table into the 4 blocks, S, P, D, and F. So you've got 26 electrons. Draw the atom first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. That's the atom. Now, that would be the orbital diagram for this, okay? Neutral atom. But for 3 plus, you're taking 3 electrons away. Don't take 3 away from the 3D, because the 3 is inside the 4. The first 2 you take away are these. That would be iron 2. And remember, iron 2 is one of the 2 ions that iron forms. Those 2 always come off first. But give it enough time, iron 2 will form an even more stable ion, iron 3, which has that one taken away. Okay? So when I say highlight the ones you're going to take away, those are the 3 you take away. When we remove that, we have a nice half-filled D sublevel. Now, if I just asked only for the orbital diagram for iron 3, these aren't there. Okay? You can lose the 4S label if you want to, but the fact is, there's nothing in the 4S. We've removed electrons from the fourth energy level entirely. So that's an iron 3+ ion, okay? Now that's a little trickier than if we were doing an anion. Because an anion, we just keep adding electrons. So let's say we wanted to do a bromide anion. Notice bromine is in the same period as iron. But by the time we get to bromine, we're in the 4p. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So let's do a bromine atom and then a bromide 1- ion. A bromine atom, after the 3d, we come to the 4p, right? So if we did a bromine atom, if you look in your periodic table, bromine has 35 electrons, okay? So, but once we get that, we're at zinc. Now we're in the 4p. Bromine has 1, 2, 3, 4, 5 4p electrons. Every halogen is S2p5. Those are on the outside. Every halogen has 7 valence electrons, just like the number of letters in the word halogen. Every halogen is S2p5, okay? And remember, S and P are the only ones on the outside. Those are the valence electrons. Okay? So a bromine atom is this. But a bromide anion has 1 more electron. That's the only ion bromine ever formed, 1-. Why does it form a 1- ion? Because now it's got the same number of electrons as krypton. 36 electrons. Okay. Now, the valence shell is filled in krypton, 4s2, 4p6, but the fourth energy level isn't filled. What else can we put in the fourth energy level besides S and P? 4d and 4f. Because in the fourth energy level, we have room for how many electrons? N is the energy level. Square it. 4 squared is 16 times 2 is 32. Right now, we've only got 8 in the fourth energy level. Then we add the 10 4d. Then we add the 14 4f. That adds to 32. So the energy level isn't filled at krypton, but the valence shell is. In other words, the S and the P on the outside. D and F are not on the outside. They're not valence electrons. Okay. Now again, that's probably more of an answer than you expected, but there it is. And you should be able to do either cations or anions. But always start with the atom first. And I would suggest when you're doing this, do it in pencil. Because if you're removing electrons, you want to be able to erase the correct ones. And if you're doing short form, do the electron configuration as atoms. And then remove or add as many as you need to for whether it's a cation or an anion. Okay? It's not really difficult, but you gotta practice it. Okay? You gotta practice it. And again, at first glance, walking in the room and looking at the board, it's like, what is that? This looks hard. Well, everything's hard until you practice. Yeah.
Is your N equals 4 in between 3D and 4P?
Is there anything between what?
Is N equals 4 between 3D and 4P?
N equals 4 is the number of N is the energy level.
Yeah.
Okay, so your question is,
Like where do you put it, write it in between 3D and 4P? Like,
I'm not sure I understand your question.
like you're telling us how like n equals 3 is like parallel to
You can put the n equals 4, I mean, put it even with the 4p if you want. This isn't that critical. It's just you're not gonna write n equals 1 here and n equals 2 here. Draw these first, put the n equals 2 halfway between the 2p and the 2s. Put the n equals 3 even with the 3p. And if you're gonna go that high, put n equals 4 probably equal to 4p. The other thing you don't have to worry about is you don't have to make them closer together. We know they get closer together. All that matters is the order, okay? Yep.
So just kind of clarify, so after n equals 2, we can just kind of put like the different energy levels like parallel with the p orbital?
Yeah, I mean, I'm probably not gonna ask you to go up to, 4F, but this isn't as critical as you kind of want it to match about evenly with where those things are. That, it's just, don't do that first, do it second. And that order is what the diagonal diagram would specify, right? But once you do this enough, you won't need the diagonal diagram. The periodic table is gonna tell you exactly. And when we go into chapter 6.1, that's 6.2, we don't want that. I've referred to this diagram before. If you read that diagram like words on a page, you get the exact order specified by the diagonal diagram. Okay, so if you drew the diagonal diagram, 1s, 2s, 2p, 3s, 3p, 4s, 3d, you get, it's exactly from this. All we've done here is put those where these are. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d. That's all this is. So, again, very, very quickly, you won't need the diagonal diagram. And a point I make in section 6.1 is the order of the periodic table, the order of the elements in the periodic table, that was basically in place before we knew anything about quantum mechanics. All quantum mechanics did was confirm what experiments had showed us. And we're not doing 6.1 yet, but we will. We'll start that on Wednesday. We'll do a little bit of history. We'll talk about some attempts by scientists to make sense out of the elements. We're going to hear a guy named Henri. There was a geologist who actually had a spiral diagram or a spiral model that kind of showed elements in the repeated properties. His name was Shanker-Trois. But it really wasn't until a Russian scientist named Dmitry Mendeleev that sort of started to work on it that we actually got what we call the periodic law. And then about 50 years later, we came up with quantum mechanics. So really 6 is really just a continuation of the end of 5. So that's why starting it is not going to really affect any of your ability to understand it. Hopefully it'll help you before we do the test. What else? Yep. Anybody besides you? There's like, what, 3 people have asked questions. Go ahead.
When we're writing the electron configuration, like drawing it, does it matter if we write in the order that the orbitals are built, or
No,
small
it
to
doesn't.
large?
You could write it littlest to biggest, as long as you're doing it past core notation. Like, littlest to biggest assumes that what's before it is core notation, okay? The short answer is no. But be able to do both complete and core. And just be careful, if you're writing it in the order you fill it, that if I ask for a configuration of a cation, that you remember where to take the electrons from first, okay? And because the periodic table's job is to predict behavior, that's why they write it littlest to biggest beyond the core, because that dictates behavior, what's on the outside, okay? Yep.
Can you re-explain how repulsive forces work in the sublevels?
How the repulsive forces work?
Yeah.
The more orbitals there are in a sublevel, the more repulsive forces exist in that sublevel. So, P, and this only applies to multi-electron atoms, because for hydrogen, because there's only one electron, there's no electron-electron repulsion. That's why for hydrogen, all of the orbitals are at the same energy. So when we go to the n equals 2 for hydrogen, 2s2p, exactly the same energy. Go to the third for hydrogen, 3s3p, 3d. There's no electron-electron repulsion. But as soon as you have multi-electrons, 3p orbitals there's more repulsive force than an s sublevel. So 2p is always higher in energy than the 2s, because there's more repulsion in a p than an s always. There's more repulsion in a d. Why? Because there's 5d orbitals. There's more repulsion then in d than p, because 5 is more than 3. And more in p than s, because 3 is more than 1. There's more repulsion in an f sublevel than a d, because there's 7. So 1, 3, 5, 7. That tells you, in any energy level, which is going to have the most repulsion, therefore the highest energy. And the energy we're dealing with here is the energy of repulsion. All right? And remember, Bohr did not see an electron as anything other than a particle, but his model didn't work really for 2 reasons. Because he didn't, and we're not faulting him because he hadn't thought of the electrons being a wave, but waves both interfere with each other, but they've also got charges, so they repel and they interfere. And that's why it gets complicated when you go to a multi-electron atom. And that's why it looks like this rather than what it looks like on. So if you look on page 271, that energy, that orbital diagram is only for hydrogen. So this is only for hydrogen, because there's no electron-electron repulsion. But for multi-electron atoms, it's a little more complicated. All right? And as I said, you don't have to put the P here and the D here and the F over here. Just stack them vertically, it's fine, okay? And you also don't have to put them closer and closer together. What else? You guys know anybody any friends in other high schools? Are they learning this? Ask them. Ask them what they're learning in Chem 11. See if they're learning this. I bet you they're not. Unless they're using our books. And about 30% of the high schools in BC do use our books. It's a toss-up, though, how many get through the stuff we get through. Yep.
What's the difference between the diagram on the board and then the one that we draw?
None.
Oh.
None, this is the same. It's just this one's prettier. But 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P.
So when,
Same order.
so when we draw it on the test, like,
Draw that,
That
don't
one.
draw this.
Okay.
Yeah. Don't draw little circles, just draw lines.
That's like six.
Some of you suck at circles, they would just get messy. Now just do this. Okay? You don't have to draw boxes, just draw a line and then arrows. All right? And you might have remembered on the second video, they actually populated some orbitals, and you could just see, with the video was kind of bad quality, but you could see the little arrows going in there. They didn't explain Hund's rule. And notice they also didn't go past calcium. Because to go past calcium, they would have then had to explain why we have 3 in front of D rather than 4. And that's because we start filling the 4th before we finish the 3rd. But they stopped there. Now, I guess the next question is, when is the test? Well, it can't be Thursday, because Thursday we have Mass, right? The next time I see you next week is Wednesday. Yes? Wednesday is probably CLE. Tomorrow's advisory. Isn't it? I think. Anybody know what we're doing for advisory? Something to do with Easter eggs? Maybe? I don't know. Remember last year they did Easter eggs?
Yeah.
Or have we done those already this year? Last year they were supposed to paint Easter eggs, but they forgot to paint. So the eggs were there, but there was nothing to do with them. So I don't know what they did. So maybe they'll remember the colors this year, and maybe that's what you guys will do tomorrow. I don't know. I think it's a safe bet to conclude, regardless of what it is, it'll probably be a waste of time. But the fact that it's happening tomorrow means probably CLE is what we're gonna get when I see you after Thursday. So it probably will mean that the Friday is then the test, I think, which I think is a full day. When are you guys going on the retreat? When? What date?
16,
some of us are
17.
gone the 15th.
So it's not a week Friday, isn't it? So you guys are gonna be here a week Friday. And as far as I know, that is a full class. So that tentatively will be when the test is. Between now and then, starting on Thursday, we're gonna start chapter 6. We'll probably get through all of 6.1 in one period, because most of it you already know. We're just adding a few historical references. So we might even be into 6.2 by the time we write the test, but obviously nothing on 6 is gonna be part of the 5 test. It's just that we can't afford to have really any more than one review class, because we got too much to do. Yep.
Do we have to know how to draw the 5 different D shape?
D orbitals?
Yeah, D orbitals.
God, no, you don't. You have to draw them. And you don't have to name them, you just have to know there's 5 of them. Okay? 1, 3, 5, 7, 1S, 3P, 5D, 4S. That's all. Mm-hmm.
Do we need to know how to calculate wavelengths using Berkeley's equation? Like, are there gonna be those calculations on it?
You don't need to calculate like of a baseball or a rifle bullet, no. But you do have to know the significance of the equation. In other words, what is this thing telling us? That's a constant, right? Another way you could write this is this. Correct? Two things multiplied together giving a constant means they're inversely related. So, this tells us as this goes down, that goes up. It tells us as that goes up, that goes down. but they multiply to give a really tiny constant. So whether you write it this way or this way, it tells you that mass and wavelength are inversely related. For things with a really, really big mass, like a felt pen, because that's so big, that has to be really small. Why? Because that's really small. That's the only thing I want you to remember about Planck's constant. You don't have to remember 6.6262 times 10 to the minus 34 joule seconds. You just have to know it's damn tiny. And that's why the wave nature of particles only applies, it's only important in this, at the subatomic level, because Planck's constant is so small. So we can ignore the wave nature of macroscopic particles because their mass is so big, so the wavelength is so tiny, because this is so small. But we can't for subatomic particles. And you may not have noticed that the vast majority of our discussion of atomic structure was about electrons. The protons and the neutrons weren't a problem. Neutrons were discovered eventually. But the problem was, what were the electrons up to? They are the things that weren't behaving the way they should. And that's really what quantum mechanics is dealing with, is about the electrons. So, to answer your question, you need to know the significance of the equation, showing us that wavelength and mass are inversely related through a very tiny constant. The other equation that needs only be considered on the order of the really tiny is the Heisenberg uncertainty equation. And again, it's got Planck's constant. And the product of where something is, the uncertainty in where something is, multiplied by the uncertainty in where it's going, is greater than or equal to a really tiny constant, Planck's constant. And that's why you don't need to worry about it when you're talking about macroscopic particles. So one of the equations that deals with electrons is a wave equation. The other equation is an equation about mass. So Heisenberg, particle, de Broglie wave, they're foundations of quantum mechanics. I found it difficult to write this at a level that intuitively kind of makes sense. I had to give you enough information, but I also had to stop at the point where it got too mathematical. And again, it's not intended to be that this is about doing calculations. It's, can you wrap your head around this stuff? And can you begin to appreciate how things on the order of the really tiny don't behave the same? And you might remember at the very beginning of this, I said one of my physics profs in third year was a special relativity course, and he said human beings live in, make sense, interpret the world that's big and slow. So for slow things, we don't need relativity. But when things get really fast, we need relativity. Okay? We need the idea that when things approach the speed of light, weird things happen. We don't need to worry about those weird things because nothing we experience goes that fast. We don't have to worry about time dilation or length contraction. And we also don't have to worry about the world of the really tiny. Quantum mechanics governs the world of the really tiny, but we don't need it because we don't experience the world that small. And that's what we're doing. That's what quantum mechanics deals with. And there's a number of weird ramifications of quantum mechanics. This is just kind of the biggest of them, okay? And imagine all those poor people in the hallway who never take chem and thinking that the Bohr model they learned in grade 10 is correct. And all those little diagrams with the electrons traveling in these little paths is the way it really is. It isn't. It's just a simple interpretation. So, and we stopped believing that in 1913. Actually, it's 2026 now. 2027, you could argue, is probably the 100th anniversary of quantum mechanics, because it really wasn't until 2027 or 1927 that Heisenberg and Schrodinger's ideas were sort of woven together. Okay.
That's what I mean. Special for once.
Anything else? We've covered a lot of ground, even though there's been very few people who have asked questions, but that's, I guess, better than no one asking questions. So, we got about 2 minutes. You can play amongst yourselves.